Hello, my name is Alexander Schatten, and the title of my lecture today is Complexity in Software, or maybe with the subtitle even Handle with Care. This lecture is in the Beyond Coding series and sort of a conclusion and wrap up too, if you want. The underlying threads of the course were long-term thinking and maintainability of IT infrastructure, how to handle complexity and resilience of software systems and IT systems. In sum, how can we provide high-quality IT services, software services, for long term in our ever more complex world? A world where software and IT is the digital nervous system that enables the services of our modern world. In this lecture today, I will try to wrap up the question what complexity means in general terms, and then also means for software systems, and provide some food for thought, discussion to contemplate in your own company, in your own environment, or to discuss with colleagues and in the team and so on. Now, the three main topics I'm going to discuss today is number one, what is complexity? Number two, why is it important to understand, especially in the software engineering area? Thirdly, how can we handle it? How can we maybe reduce complexity? And how can we create high quality software systems that operate and can be maintained for a long period of time? And I would like to start with two quotations. The first one is from late Frank Schirmacher from his 2013 book Ego. He writes, "In the meantime, phenomena were appearing that used to be called natural phenomena, but of which we now do not actually know who or whether anyone at all had caused them." So what does he mean? Like, we observe in our technical, in our social, in our societal environment, phenomena that we maybe in the past knew as natural phenomena that we couldn't really associate with some concrete cause. But now we realize this phenomena in our techno-social world. And it's often hard to realize, did anyone cause that and who would that be? And secondly, quotation from Stanislav Lem about 30 years earlier, from 1983, from a rather obscure book of his. And he writes, "Tremendously fast systems make mistakes tremendously fast. Where fractions of seconds decide, it is impossible to achieve military strategic certainty, or in other words, one will no longer be able to distinguish between victory and defeat." Now, this is a bit of a military language here because of the topic of the book, but we could argue, like, if we make automated processes, software, IT systems that make decisions and take people out of the loop, people who before maybe thought about something, made a decision and slowed processes down, we suddenly come to systems that are really fast, and every decision can also, every mistake can also go through the system, run through the system and propagate very fast. And victory and defeat, we could say, like success and failure. So success can be fast, but failure can be also very fast and very hard to control. And we talk about such issues later on. And finally, I very much like John Gall, which will bring one or two quotations in this lecture. And in his book Systematics in the 1970s, he writes two things. Number one, things aren't working very well. And secondly, complex systems exhibit unexpected behavior. And I like this because I'm actually quite certain that most people in IT would probably agree with these two statements. Things are not working very well and complex systems exhibit unexpected behavior. Okay, let's go now into the first question. What is complexity actually? And let's start with some basic terms. First of all, there are two terms, namely complex and complicated. And these two terms are often used interchangeably or in sort of an interchangeable way in normal language. So people say, "Oh, this is complex." But actually, there's a significant difference between complex and complicated. And the associated terms, simple and easy. We'll get to that in a moment. Let's start with the term complicated. Complicated is a relative term. So something is complicated for someone. So something can be complicated for me, but easy for you, and vice versa, obviously. So complicated is, in fact, not a systemic, not a generic independent description of something, it's a relative one. Now, the opposite of complicated is easy. And as we see in this figure, easy is something that is near at hand, familiar, near to our capabilities. Again, relative. It can be easy for me, complicated for you. Now, if we go to the systemic terms, we come to simple and complex. And the opposite of easy is simple. Simple in systemic sense is not a relative term. It means it is something that encapsulates one task, one role, one concept, one dimension, something like that. And complex, on the other hand, is the opposite of simple. Now, what does it mean? Complex, again, is a systemic property. What constitutes a complex system? Well, it's not such an easy question, but we can agree on a number of factors that are usually described like that. Number one, a complex system typically has many parts, many actors. And these parts or actors interact with each other, or many of them interact with each other. And the interaction is often more important than the state of the individual actors or individual parts. And with the interaction or during the interaction, the actors can change their status. Of course, a complex system develops usually among certain boundary conditions. So for instance, it can be natural laws, it can be biological laws, conditions, or also technological conditions, technological setup. Now, when we look at this figure, we see the interplay between all of these four parts. Okay? We see simple as opposite to complex, easy as an opposition to complicated. And on the left side, simple, complex, the systemic terms. On the right side, easy, complicated, the relative terms. We are going to revisit this idea a bit later again, okay? Now in this diagram, I try to outline that systems can fall typically in one of four categories. A system can be easy and simple, a system can be simple and complicated, a system can be easy and complex, and a system can be complicated and complex. Easy and complicated, again, are relative terms. So for instance, easy and complicated might refer to me, right? So for instance, a simple and easy game would be something like Angry Birds or Mensch ärgere dich nicht, a simple board game, or one food stall, one fast food stand, for instance. Why? Well, easy. It's easy to learn, easy to understand. You don't need a long education to operate a fast food stand. To buy sausages, fry them and sell them, or to buy beer and sell it is a relatively easy and simple process. Also, simple games like Mensch ärgere dich nicht, you can teach this board game to, I don't know, a 4 or 5-year-old child probably, and it will be able to play this game in a relatively quick, short period of time. Now, the dynamic of these games are relatively simple. There's not a lot of surprise in these games. It's relatively clear what's going to happen. On the other hand, a system that's easy and complex could be, for instance, a game like chess. Chess is definitely more complex than something like Mensch ärgere dich nicht. On the other hand, it's still relatively easy. If I have never played chess before and you're a chess master, you probably can teach me chess within like 10-15 minutes. Teach me in the sense that I understand the rules, that I can play the game with you. I can play the game with you according to the rules. Now, will I beat you in this game? No. Why? Well, opposed to Mensch ärgere dich nicht is not a game that is just essentially based on luck and simple moves. It's a game that is relatively easy to learn, but develops a complex interplay between these figures, and you have strategic and tactical components, and all of that require more elaborate pattern recognition that you have to learn over years and years. And when you're a good chess player, I might need years to learn the game to maybe at one point in time be able to challenge you. And in the right upper corner, we see systems that are simple and complicated. So this means they are harder to understand for many people, but still systemically simple. For instance, a mechanical watch. If you're a watchmaker, of course, the mechanical watch might also not be complicated for you. It might also be easy for you. But for most people, I would say to understand how a mechanical watch works when it's not working anymore, to repair it would probably not be an easy thing for most people. At least for me, it would not be. So it is, in a systemic term, simple. It is deterministic. It has some mechanical parts that interact in a deterministic way. And the behavior of the watch will never really surprise you, right? So in the sense, what can a mechanical watch do? It can stop, it can work correctly, it can go too fast, it can go too slow, but that's actually it. It will not surprise in the sense that it's now 11 o'clock and a second later 4 o'clock. So this will not happen with a mechanical watch. So such type of systemic emergent behavior, something that you will not observe there. And in the right lower corner, you see systems that are complicated and complex. So for instance, biological ecosystems, a rainforest, a lake, but also technical things like the internet, for instance. We are going to come to that point a little bit later. The internet is a technical system, but it's made of a large number of nodes with services on these nodes that interact in ways that are hard to understand, and they create emergent properties, and we'll come to that a bit later. Now, interestingly, you can see I have certain systems that are in both in the top and in the bottom area, like in simple and complex. For instance, on the left part, we have one food stall, so one fast food stand. And then in the complex part, we have a system of fast food stalls of a city. And there's a clear difference. In one alone is simple, but all fast food stands in the city, now we have a complex systems because we have an economic perspective of that. Maybe the questions, where is your stand located? Do people like to go to the other stand more because they like the different fast food or stuff like that? And now you have an interaction between all of these fast food locations. And this interaction now is sort of complex, like all restaurants in the city, right? One restaurant, relatively simple, all form a complex system. And the car is also an interesting example. An old car, like a car from the 1970s, is essentially like a mechanical watch. You have a mechanical system that works more or less, actually more deterministic, and the behavior of the car is essentially defined by the driver. The driver defines essentially how fast the car goes and in what direction it goes. Now, this is not necessarily true anymore in our time. Why? Number one, the car became much more digital in many ways. So we have a car today is a driving computer essentially, right? We have a lot of systems, electronic systems that control the engine, that control a lot of entertainment systems and whatnot in the car. But more importantly, we have assistive systems like systems that avoid crashes or that keep you in the lane or that help you with navigation or that communicate with the car manufacturer to figure out if there are software updates, all such things. And this means that the behavior of your car is now not entirely dependent anymore on the driver, but it's dependent on the interaction with other systems. And of course, the same is true for car traffic. Car traffic is essentially an emergent property of many, many cars that are on the road and behave in a particular way. We will come to that a bit later. And the interesting thing now about this diagram is, and it's not very important, by the way, to take this diagram literally. Maybe revisit it after the lecture and just think about it. Maybe replace systems here with your own ideas and just think about it. Does it make sense to you? What other examples would come to your mind in the particular quadrants and so on and so forth? Now, the interesting part now about the complex and complicated systems is that a complex system can be highly resilient or robust, and it can also be very fragile. And what we see is that, for instance, most or actually all biological systems are generally very resilient. Why? Because they emerged over long periods of time during long periods of evolution, and all of the fragile parts died out already in the past. That doesn't mean that they are invincible, of course, but they are relatively and quite resilient. We also have technical systems that were very cleverly designed, like the original ideas of the internet. The original design of the internet is a protocol where you have nodes and you have a routing principles that allow for the removal or destruction of some nodes or many nodes even, and still the system can work properly with the remaining nodes. Now, why did I make an error here from the left side, from resilient to fragile? Well, because we still have, of course, the fundamental protocols of the internet in place, but a lot of the practical services today are dependent on a small number of service providers, like the big cloud providers, for instance. Now, what did we do? We moved from an internet of a large number of distributed nodes, where each node might get out of service, but the rest continues to work, to an internet where a large number of services dependent on this small number of cloud services. Now, if one of these cloud services has a problem, a large number of our internet services run into problems. So actually we created, or we shifted the system from complex and resilient to complex and relatively fragile. And we can discuss this about other systems as well. Now, how do we get from complicated to complex, or from simple to complex, to be precise? Well, there are different reasons for that, and we'll get to that later. So one reason can be bad engineering, that you add complexity into the system by bad architecture, bad engineering. Scaling effects, larger interactions and so on, we'll get to that later, can also increase the complexity of the domain and of the architecture. Now, what you see here is like visualization, just as one example of parts of the internet, and you see exactly like this fractal pattern that we see here looks a little bit organic, like, I don't know, like tree branches or something like that. And this is sort of a visualization of parts of the internet, a set of internet nodes. And you see a lot of small nodes that are connected, and the bigger nodes and so on. But there are a lot of ways to come from one part of these branches to the other part. So this is actually quite a resilient structure in the original conception. Now, we should mention another concept in that area, which is quite common in complex systems, and these are feedback loops. Feedback loops are often critical and are leading to higher order or emergent behavior. What is a feedback loop? A feedback loop essentially means that the effect or the outcome of a process feeds back directly or indirectly to the initial process. We know this in a lot of industrial processes. We know this in nature, predator-prey dynamics, for instance. But we also know it in our management processes, for instance. Think of processes like Scrum. Scrum goes back in the core ideas, goes back to things like the plan, do, study, act idea, which is like decades old, and this illustration or this figure shows you what this plan, do, study, act essentially means. And it means like you start with a mission, with a vision, you plan how to do it, you define some indicators, then you do it, and then you check if you go into the right direction. And if you don't, or if you do, if you don't, it depends, then you act on your evaluation, and you go again into this circle. So this is a constantly iteration, sort of a closed loop that goes on and hopefully continuously improves your system towards the vision or mission that you have. And complex systems are also often linked with chaos or chaotic behavior and self-organization. What is self-organization? Self-organization is often referring to bottom-up organization. So systems organize bottom-up and not top-down by top-down defining how the system is supposed to work, but more like a bottom-up organization. We'll get to that a bit later too. And we also see often dynamic stabilization, and as a consequence of that, resilience in complex systems. What is dynamic stabilization? Let's say you have static stabilization or dynamic stabilization. Static stabilization would be if I use a tripod and put my camera on the tripod, then this camera is statically stabilized. So it's on the tripod, okay? A dynamic stabilization would be if I hold the camera in my hand and try to follow a motive and try to stabilize it with my hand. Or you can imagine a helicopter, a pilot who tries to keep the helicopter on a particular position. The wind might change and so on, and the pilot has to dynamically adapt whatever he does with his gizmos in the helicopter. I am not a pilot, to dynamically stabilize this helicopter in the particular location. But of course, we also see dynamic stabilization, for instance, in cyber threats and defense. You have systems, problems are revealed, criminals try to exploit the problem, so you have a cyber threat that is exploited, and on the other hand you have the defense, the people who try to defend the systems and try to patch it and try to do countermeasures against the attacks and so on. And this is also sort of hopefully a stabilization in the sense of that the defense is maintained. If the defense is not maintained, of course, if the attack goes through, then we are not stabilized anymore, then we lost this particular fight. How this bottom-up organization, how this emergent behavior can look like, can be seen on this murmuration behavior. I like to show this video because I really like this type of flocking behavior very much. It is, you see starlings, and the starlings, each starling interacts by observing the starling beside them, observing like in a metaphorical way, and then redirect their particular flight according to the others around them. Of course, the behavior of the one starling again affects the other ones and so on, and this leads to this flocking behavior, which is quite amazing. And of course, we do not only observe these type of organization in nature, but we also see it in our society. This is, for instance, an example of a crossing in I think, Tokyo. And we see certain boundary conditions, like technical boundary conditions in the sense of there are traffic lights and there are some structures. But how exactly the flows of people and cars operate to use the place, to use the space, to go in the direction that they want, is sort of a self-organizing process. There's not a person who tells each car and each passerby how to move in that particular situation. When we go now towards emergent behavior in software systems, so because we are actually interested in software now, and we observe self-organization and emergent behavior also in IT and software systems. For instance, consider machine learning, or what is also called artificial intelligence. Machine learning means you have sort of a black box algorithm, some network or something like that, and this network tries to stabilize its behavior according to input data and target values. And it tries to organize itself according to these conditions. And of course, the data can change over time. When the reality changes, then the algorithm has to maybe relearn and change its reaction towards the target system. Or we have agent-based systems, something like self-organizing swarm drones. You have drones which you would like to fly in swarms, like a little bit similar to the starlings that we've seen before. And you do not top-down define where each of the drones is supposed to fly, but the drones try to follow a general goal, but then in detail organize themselves according to their local environment. But we also see this type of emergent behavior in socio-technical systems, so in systems where humans and technology is sort of connected. Think of shitstorms, for instance, or trends on social media. This is a mixture of algorithmic consequences, like an algorithm decides that something is popular and is trending now, and by making it trending, of course, there's a self-reinforcing loop and the trend goes up. And also social interactions among people who like stuff or dislike stuff and so on. So we have this interaction between people and algorithms, technical systems that lead to this particular outcome. Or predator-prey dynamics, for instance, as I mentioned before, with security exploit, like you have threat, you have defense, and this is also, they have also emergent behavior and self-organization. There's no top-down organization of defense, for instance. We also see emergent behavior in IT-driven systems, so systems like that are highly dependent on software and information technology. The electricity grid, for instance, is a good example, because we don't have like one producer, one power plant, and one consumer, but we have like a number of producers and a number of consumers. And with more and more unreliable sources, production sources, producers on the net, and also the change in consumption during the day, during the week, and so on, we have like a constantly changing dynamic of production and consumption, and that has to be made fit. So this has to fit together, and there is of course a lot of dynamic controlling that has to happen to balance this out, and of course a lot of software is also used for that. Then we have import-export dynamics. We import electricity from other countries. We have power markets, trading systems. So this also means like not only do we have technical conditions, we also have financial and economic boundary conditions that also influence this whole market. So you see, this is quite a complex dynamic system that has to be dynamically stabilized. Otherwise, we would have power outages and stuff like that. Or cars and car infrastructure. Modern cars, as I mentioned before, are actually computers, networks on wheels, and they are connected with a lot of other systems and are managed over networks and so on and so forth. And another social example is, imagine touristic locations, like for instance, look Roy's Peak in New Zealand or Mount Everest, and look for Instagram, for instance, and you will see queues of people, hundreds of thousands of people who are queuing in front of a particular touristic spot to go there and make a selfie or make a photo of the spot or whatnot. And why are there hundreds of thousands of people queuing there? Well, maybe they saw this particular spot on Instagram or some other social network and said, oh, I have to go there, I have to see that. And then, of course, they queue with a lot of other people who want to go there, and then they make their own photos. And by making their own photos, they can reinforce that, and maybe more people are coming. So you see also here emerging behavior that then influence touristic destinations and so on and so forth. An interesting aspect now is when we are in complex systems, we suddenly see suddenly problems of a different kind come into play or appear. And I would like to visit an idea that's called wicked problems, that goes back to a paper from Riddle and Weber from 1973. And they essentially distinguish between two different types of problems. They call tame problems and wicked problems. Let's start with tame problems first. Tame problems are problems that are sort of deterministic in a way. They have a clear solution, and it's something like solving an equation or analyze the structure of an organic molecule. It's quite clear the organic molecule has a structure, and when you analyze the structure, when you figure it out, then you know what the structure is, and it can be right or wrong. Or you have a mathematical equation and you can solve it or not solve it, but if you solve it, you know if it's solved or not. Or another example that's here on this figure is, for instance, a chess problem, like checkmate in 5 moves, or this crazy example here, mate in 267 moves. I have no clue how this is to be solved, but I'm sure there is one solution, and if you figure out the solution, that's that. And you can figure out if it's right or wrong. So this might be complicated, but they are tame problems. Now, opposed to tame problems, Riddle and Weber describe that in complex environments, we start to see problems of a different kind, and they call them wicked problems. And there are a number of attributes, a number of characteristics that these wicked problems have. Let me outline them. Number one, there is no definitive formulation of a wicked problem. There's no simple test and no enumerable set of solutions. This means very often such problems, such wicked problems in complex systems are of the kind that it's even hard to describe what the problem actually is and what the solution exactly would be. So often we already fail in that particular first step. So from that it follows that it's not easy to say when the problem is solved. And then we come to the second characteristic. So then there is often no clear stopping rule or simple true-false solution. So what happens in reality? The solution approach is often stopped when the resources run out or when the new state is good enough or better than before. Situation is better, good enough, we stop it, right? The next characteristic is that wicked problems tend to be essentially unique and not open to trial and error. This means it is not necessarily a problem where you can apply a solution from a different problem and just say, yeah, we had this problem there, we apply it here, right? So it's not like in chess, end game of chess, and you have like this and this type of figures, and there's actually quite a clear description for a number of end games, how they can be won. These would be tame problems where you can learn from the one situation and apply it directly to the other one. This is not what you can do on wicked problems. So trial and error do not work well. They're often one-shot operations. So this means like the result from one problem cannot be easily refined to another. And of course, additionally, when you try to solve the problem, you change the system, and a second attempt is not possible anymore because you change the system away from the original problem. And the second attempt, you cannot go back to the original state easily or not at all. And four, a wicked problem extends laterally and vertically. So that means it can be seen, for instance, as a symptom of another problem, or it can be the source of another problem. So it can be in a chain of problems. And then, of course, it becomes often hard to figure out, yeah, what is the root cause of the problem? Because you do not want, on the one hand, you do not want to just treat symptoms, because that is not sustainable. On the other hand, it's often hard to find the root cause, so people can get lost in the attempt to find the root cause. You probably know the term analysis paralysis. So like people are paralyzed by the analysis because they try to find the root cause and take so long that the whole system moved already away probably from the original problem. So you see, it can be very hard to find the right level of approach to try to quote unquote solve the problem. And a nice quote from this paper is, under these circumstances, it is not surprising that the members of an organization tend to see the problems on a level below their own level. So it's like the typical manager saying people beyond them are always the problem. They're like incapable but not, but they themselves, of course, are not the problem. So, but this course, of course, works the other way around too. Everyone says, yeah, but the person, my manager is incompetent. So it's always the other level is always incompetent, but not oneself. So this is the lateral and vertical extension of the problem. And a consequence of that would be, I would personally even put into question the term problem at all. I would say in nearly all interesting, relevant problems that we have, the term problem probably is not appropriate anymore. Why? Because the term problem suggests problem solution. The term problem suggests here's a problem, there's a solution, the problem is solved. Now, if we follow the idea of wicked problems, we see, well, often there is no solution. Decisions in complex systems rarely lead to something that we could call a solution. It often has upsides and downsides, side effects to other systems, unclear effects, long, short-term effects, unpredictabilities, different effects on different stakeholders, meaning what could be good for the one could be bad for the other. So it's rarely that you can define a solution where everyone agrees, yeah, that's it, That's where we want to go to. And this makes it hard, in my opinion, or rather not a good idea to use the term problem. We should rather talk about dilemmata or polylemma, if you will, or alternatives with advantages and disadvantages for different people. So now a question that arises from here is, when we deal with complex systems, what does stability, prediction, and control mean? Well, as I mentioned already before, Gall said complex systems exhibit unexpected behavior. So this means in dynamic complex systems, there's usually no long-term predictability. Even control or management schemes that depend on models or prediction will fail. So this means if you have a management paradigm, a management idea, when you think you can plan long-term because you have a lot of indicators, you have models, it will most likely fail in a complex system. You will not be successful. So what does this mean? Does this mean that complex systems are entirely unpredictable, are randomly? No, it does not mean that, but they show different types of stability, and stability in a more dynamic way. And one term that we might want to introduce here is the term attractor. An attractor is sort of a dynamical stabilization of the system that is defined by boundary conditions, by system interactions. For instance, think of a climate: spring, summer, autumn, winter. Now, let's say Vienna in winter. Well, I cannot tell you how the 5th of January 2025 will be in Vienna, what temperature it will be, but I can pretty certainly tell it will not be 35 degrees, right? On the other hand, the June 10th, 2027 will certainly not be -5 degrees in Vienna. So you see, seasons tell us, well, the system will most likely be in that and that range, but we cannot say in detail. This is often a characteristic of an attractor. Also, a characteristic of an attractor is that disturbances can be balanced out by the system to a certain extent. Let me illustrate this with a nice example that is actually quite an IT-based example, if you will. It is from Stuart Kaufman. What we see here on this figure is 3 bulbs. Bulbs is means like a light bulb that can be on and off, or you can also simply see it in a purely computational sense. It's like something that's a bit 1, 0. Okay. Now these 3 light bulbs can be in the state 1 or 0, and they are connected with each other. Each of these bulbs is connected to the other 2. Okay, so far so good. Now, what we want to model now is a dynamic in time. So these 3 light bulbs have a particular state, on or off. And the question is, how will be the state of each of these lamps in the next time step, so to speak. And we have different logic how each of these bulbs develops from one step to the next. Bulb 1 operates with AND logic. AND in the sense that bulb 1 will be 1 in the next step if and only if both of the other bulbs are on. So it's 1 if the other 2 are 1. Bulb 2 and bulb 3 operate both in that example on the OR scheme. So bulb 2 and bulb 3 will be on in the next step in time if one of the other 2 bulbs is on. You see this on these tables that are on the figure. Okay, that doesn't sound too interesting so far, but it becomes more interesting when we go now and analyze the behavior over time. So as we only have 3 bulbs in this simple system, we can outline the complete all possible options. So you see on the left side, at the time t, we have bulb 1, 2, 3, and then we have all possible options, all possible configurations. And on the right part, you have t+1. So the next step in time, you see how it changes from left to right. So for instance, when when all three bulbs are off, 0, 0, 3, 0, then in the next step in time, they stay still 0, 0, 0. Now let's look what this means from an attractor point of view. Now, as I said before, 0, 0, 0 stays 0, 0, 0. So this is an entirely boring dynamic. It stays, all three stay off. Fine. Now what happens if we start from 0, 0, 1? So bulb 1 and 2 are off and the third one is on. Well, according to the table on the left side, 0, 0, 1 moves to the state 0, 1, 0, and the state 0, 1, 0 again moves back to the state 0, 0, 1. Now we have, in this particular case, already an attractor that flips between these two stages. Left, right, left, right. Okay. Now go to the next example. Let's say we start from the state 1, 1, 0. What is the next state? Well, we can look at the table, right? In the left table. So what do we see? We see the next state is 0, 1, 1. Okay. Now, also from state 1, 0, 0, we get to 0, 1, 1. And also from the state 1, 0, 1, the next step in time is 0, 1, 1. So interesting. So the state 0, 1, 1 sort of pulls three different states to himself, so to speak. But it doesn't stay there. The state 0, 1, 1 in the next step goes to 1, 1, 1. Interesting. And what happens is 1, 1, 1? Well, 1, 1, 1 is now a point attractor. It's like 0, 0, 0. 1, 1, 1 remains at 1, 1, 1. So we could say 1, 1, 1 is an attractor. It attracts various states of the system, namely 4 states, 1, 0, 0, 1, 1, 0, 0, 1, 1, and 1, 0, 1. All of these are attracted towards the state 1, 1, 1 because it sucks, so to speak, those states into 1, 1, 1 and then stays there. Okay, you see this is a point attractor. But now it gets even more interesting. Can we say something about the stability of the states? Well, the first state, the 0, 0, 0 state, is quite unstable to perturbation. What does it mean, perturbation? Change any of the 3 bits. So change the 0, 0, 0 to 0, 0, 1 or 0, 1, 0 or 1, 0, 0 and you will see that you leave this attractor. For instance, 1, 0, 0 and you jump into the attractor on the bottom. 0, 0, 1 and you jump to the second attractor and so on and so forth. So you change 1 bit, you flip 1 bit and you completely leave the attractor. So this one is quite unstable to perturbation. The bottom one, though, is quite stable to perturbation because when we are in the final state 1, 1, 1, we can change any of these 3 bits. So for instance, the first one, 0, 1, 1, what happens? 0, 1, 1 is the middle one and we go again back to 1, 1, 1. What happens if we change the middle bit? 1, 0, 1. Well, 1, 0, 1 is the lowest one. 1, 0, 1 goes to 0, 1, 1 and then again to 1, 1, 1. So also the flipping the middle bit in the end comes back to the point attractor. And the last bit, 1, 1, 0, is the one on the very left and again flows, so to speak, to the attractor 1, 1, 1. So this 1, 1, 1 attractor is quite stable to perturbation. Now, this is of course a quite technical example, but it gives you quite a nice idea of some core characteristics of attractors in complex systems. Think about this and think about other real-world systems where you might observe this type of behavior. So we have, for instance, such attractor-like situations in software engineering. Let me give you some examples. Company culture, for instance, team culture. When you go to different companies, you see that different companies have different cultures, different team cultures, different company cultures. And such a culture attracts certain people and does not attract other people. So this means you get rather a particular type of person in a particular corporate culture. Someone who feels comfortable in an insurance company probably doesn't feel comfortable in a startup company, for instance. Different cultures. If you want to change a culture, of course, This is nothing you can do easily from one day to the next, because you have people who sort of live this culture. This is why it's so hard. This is why change programs are so hard in companies if you want to change a culture in a company. But also technological conditions can be seen as attractors. You could imagine usage of a particular framework. Yeah? Let's say you use SAP, or you do not use SAP, you use Oracle, or you use Postgres, or you use Spring, or any other framework, and you build your application around this particular technical infrastructure. This leads to a particular type of architecture, to a particular type of system. Now, if you want to change from this system away, it will not be easy, because this old attractor now has a lot of pull towards itself. Imagine like you have a team where a particular type of framework was used because one particular developer introduced it and everyone followed it. And then this developer leaves and the rest of the teams decides, well, this old framework is not appropriate anymore, we want to change it. You can do it, but a lot of the architecture, a lot of the concrete implementation will be built around these original frameworks, and will not be easy to move away from the one attractor to the other. So let's take some, let's say, take home questions from what we talked about so far. What questions could this be? For instance, ask yourself, what is fragility? What is robustness? What is resilience? Especially in your systems, for instance, in your software systems. Or you could also flip it upside down. What is a failure? How do you define failure in your system overall? Or maybe more importantly, as we will see later on, how does a system react when components fail? When do we have reasonable control over a system? So what is our concept of stability in a system that we do not have completely under our control anymore? Because we might use cloud systems, we might use distributed systems, we might interface with systems from other people, from other companies. So we don't have everything in our control anymore. So what is our concept of stability? So maybe one lesson that we can try to learn, and we will get to that again a bit later, is we often cannot put odds on the unknown, but we might be able to prepare for the effects of the unknown. So we might not predict what's going to happen, but we might prepare for the effects of the unknown. That's quite an interesting idea. We will get to that a bit later. Right. Now, let's ask ourselves why all of that is important. How complex IT interacts with other parts of the world. Again, to wrap up what I said in the beginning, ICT can be seen as the digital nervous system of our society. But just because we can build something doesn't mean we do it right. George Dyson, for instance, had this nice quote. He said, there's no law against building something without understanding it. And unfortunately, I think a lot of people who are in IT pretty much know what he's talking about. It seems that we're constantly building stuff that we actually don't understand. And that can be quite a problem, considering the fact that these IT systems that we build become more and more essential for our society. Let me give you some examples. For instance, supply chains. We have supply chains that run over the whole world, that include hundreds or even thousands of suppliers. And our production sites, our retail, our medical system is dependent on the functioning of these supply chains. Energy supply, as I said before, I just remember the example of the energy grid. Complex system. If anything fails there, we have power outages, we can have power outages, and this can be very destructive for our society. Financial services, insurances. I'll get to an example of that later. Tourism, of course, as I mentioned before, or military. Military systems are today full with digital technology. And if you don't really understand what's going on there, well, that's not very good, clearly. So we can say as soon as something is touched by ICT, it becomes more complex. Why? Well, I would say we can say at least three different reasons for that. Maybe more, but at least three come to my mind now. Number one is the level of connectivity. As we said before, a system tends to become more complex when it has more nodes, more connections. Connections make a system more complex. Now, with IT, clearly we connect systems that were not connected before. So level of connectivity. Second, speed. Speed can be a real problem. Decisions are made, decisions can mean automatic decisions from systems, and they propagate through the system without probably any person in between intermediating that. And of course, the distribution. Often our systems are dependent on the results, the services of other systems that can be on the other side of the planet. And this distribution, of course, makes it also less clear what happens where, when, how. Right. Now, let's go back to complexity in software. What does it mean? Let's first ask the question, how does complexity come into software? And I think we have to distinguish three different types of complexity, if you will, or three different sources of complexity is maybe the better description. Number one is we have a complexity in the domain. We write software as a service for a particular domain. Okay, let's assume we want to write software for a company that has an international supply chain with hundreds of thousands of distributors and people who are parts that are involved, from shipping to producers, whatnot, and you want to have a software that manages this or organizes this supply chain. Well, then you have, if you want such a supply chain, such a complex supply chain, then you have the complexity in the domain, in the problem. And this complexity, of course, you're not going to get rid of by making a software that tries to deal with that. So you have complexity in the domain. But you also have complexity in the software itself, in the architecture. So you can program, you can develop it better or worse. So in the worst case, you have a lot of complexity in the domain, and on top of that, a lot of complexity in the implementation of the software. This makes the whole system even more complex. And of course, thirdly, we have a process of making software, of making products, of making processes. And this process of making things, the human interaction, the management, the decision making, the financial impact, all of that is another level of complexity that interacts with the other two aspects. Now we can ask the question, what increases complexity in software? I mentioned some of these aspects already before, but let's maybe conclude it a little bit. Scaling. The bigger, the more nodes, the more contributors, the more actors, the higher the complexity typically. Interconnection, the more connections, the more complexity. Speed, how fast are these actors, these parts of the system interacting. Number of stakeholders, users. How is the system designed? Is it designed by committee? Is there the attempt to top-down design a complex system? This will most likely fail. Do you have a lot of overreach by governance, legal aspects, fear-driven management, all of that stuff? Where there's an attempt of a command and control management, which is simply not working in that type of systems, then you again created actually more complexity and you make it harder than you actually should. And of course, technical architectural mistakes. To the management aspect, I come a bit later again. What decreases complexity? Small focus code. So generally spoken, code is not an asset. Code is a legacy. A lot of code is nothing to be proud of. The smaller the code that solves a particular problem in general, the better. Few dependencies. The more dependencies, libraries, external services and so on, the more dependencies, the more complexity. Fewer dependencies, less complexity. Few interactions, less complexity. Clean code, clean design made by few people in an evolutionary growing process that we might come up later again. And of course, also compartmentalization and decoupling. Now, let's revisit again the effects of software. Why is complexity in software potentially a problem? Well, one reason clearly is that cause and effect can become unclear. There's a nice quotation from Mitchell Resnick from the MIT Media Lab from 1994, so quite some time ago, but he already brings it quite to the point. He says, people tend to look for the cause, the reason, the driving force, the deciding factor. When people observe patterns and structures, or also problems, in the world, they often assume centralized causes where none exist. And when people try to create patterns or structures in the world, they often impose centralized control when none is needed. And I would even add, not only is it not needed, it doesn't work. Right? So, in other words, we have not learned how to handle, how to control complex systems. We either try to top-down define them, top-down manage them, or search for the cause, the reason, the driving force, and so on. And this is also according to Resnick a problem. So, and if cause and effect become unclear, this can be, of course, a problem for a number of software systems, which can lead, particularly when we have unclear dependencies and interactions, it can lead to loss of control. And it also, complexity can lead to emergent behavior, as we mentioned before. But let's again distinguish among two types of emergent behavior, because there's emergent behavior that is desired and emergent behavior that is undesired. So, for instance, what can be desired emergent behavior? Well, for instance, agent-based systems. Remember the flocking birds, right? If you want drones that coordinate themselves like flocking birds, then there's sort of an emergent behavior behind it. You on purpose do not want to control in a top-down manner each individual drone. You want a sort of self-organization. This is emergent behavior, but one that is as designed, if you will. Machine learning, artificial intelligence in general, if you want to have systems that learn how the real world works and also changes, then we need a certain amount of emergent behavior to be allowed for. On the other hand, we have a number of undesired effects of emergent behavior. For instance, when we have unclear system behavior in areas where deterministic behavior is expected. Assume medical devices, for instance. You have a medical device that's assumed to do a particular job under particular conditions. You do not want the system to behave, I don't know, sometimes like this, sometimes like that. You want a clear deterministic behavior. There are systems that should work in a particular way in a particular situation. You do not want unclear cause and effects there. We can see loss of control over entire system landscapes. This is clearly also not desired. We can have security issues, bugs and data loss that is very hard to figure out where it comes from, where the security bug comes from, where the bugs come from, where the data loss comes from. This can also be emerging effects from the loss of control of our complex systems. Now, let's go into a number of examples, a number of security examples maybe. For instance, we had recently the Log4j library issue. And that's insofar interesting. One, because Log4j is one of these libraries that a lot of systems have in their dependencies. And it's actually a low-level library, if you will, a technical library, something programmers use to log the state of the application. Nothing that you would actually put too much weight on in general. But what happened here is there was a significant security issue, and the system suddenly did things that developers, or most developers, probably didn't expect. There was a problem with some lookup interface, and this lookup interface allowed essentially to break out of the local context and pull essentially a lot of external code and external access to your system that you never would have expected. And this is interesting because this is one library that is extremely popular, and the security problem came from a location where you wouldn't expect it actually. And suddenly you opened up a system to quasi public access that was never intended to happen. Let me give you a second example. Coming back to an example we had before, cars, infrastructure, and the internet. Cars today are, like, as I said, driving computers, driving network machines. And there's a recent analysis by security expert Sam Curry, and he analyzes critical vulnerabilities in cars of more than 15 different manufacturers. The link to this report you can find also in the show notes. And this is quite interesting because 50 different manufacturers are really a lot of manufacturers, and we see a wide range of different attacks that are possible. Not only one attack vector. It wasn't like they used one library and this was a problem, but there was a wide range of attack vectors. So we have a broad range of vulnerabilities, and this is a sign of not an isolated or of a located problem, but of a systemic problem. So this means a lot of these companies simply seem to have lost the control of their software and the complexity of the software, and so they opened up backdoors and problems in their infrastructure, partly in the infrastructure, partly in the cars systems, that allowed for attacks of a wide range of possibilities. I'm not going to name the car manufacturers here, but let me just tell you a number of attacks that they could successfully do. Full remote lock, unlock, engine start, engine stop of a particular car of a particular manufacturer. Also, the ability to locate cars with precision, individual cars. Access to hundreds of mission-critical internal applications of a car manufacturer. Or send vehicle commands, retrieve customer information. Possibility to completely take over the accounts of employees of the particular car manufacturer. Or in one case, quote, full administrator access to a company-wide administration panel with ability to send arbitrary commands to an estimated 15.5 million vehicles. Unlock, start, disable starter, etc. Read device location, flash update device firmware. So in other words, the ability to full takeover of fleet of cars. So you see, these are not isolated things. We clearly have a systemic problem here, and not only, of course, in the car industry. This is just one current example. But also we see everyone who is in IT knows of a large number of projects that has had massive project overruns or completely failed. Hundreds of millions of euros that were invested to try to change one system to another one and failed. Or another effect, unclear behavior of software systems. Let me give you another example here, or two examples here. One is microservices. There's quite an interesting report by Uber, and you will also find the reference in the notes. Microservices started as an idea of decoupling to better manage systems, to better roll out, to better administrate systems. And they are a good idea in many cases, but when you overdo it, when you suddenly have hundreds of thousands of services, suddenly companies figure out the idea of isolation, of we have a compartmentalized system, is not true anymore. Suddenly you figure out, when I change this one service, this one microservice, dozens of other microservices are affected as well. And I don't even know which ones, because I cannot easily figure out how the communication flow goes. So from the monolith and the complicated structure of a monolith, we went to a distributed microservice architecture in some cases, where the coordination creates a complexity that might be even worse than what we have seen in some monolith. So this is not to say that microservices are per se a bad idea, but it shows that when you do it wrongly, you can get complexity in by the backdoor that you never expected, and suddenly you again lose control of your system. Another good example is the so-called flash crashes in finance. For instance, there was a big one in 2010. There were later ones. We see them actually every some years. And for instance, in May 2010, there was a flash crash, quote, in which a small disruption quickly spread to hundreds of stocks that plunged sharply, so to as low as a penny, only to recover moments later. It was one of the strangest days in Wall Street history, and that's saying something. Chris Clearfield in Meltdown. So what happened here is not entirely clear. To try to analyze it later on, but what seemingly happened is that we had a runaway effect from trading algorithms that were programmed to sell and purchase particular stocks, and somehow there was a feedback effect that ran amok, if you will, and suddenly there was a flash crash that was entirely unintended, destroyed enormous amount of money, but in that case it came back seconds or minutes later, but still clearly behavior that was neither intended nor desired. Okay, now to wrap up our lecture, let's come to the last aspect. We talked a lot about what complexity is, what effects it can have in IT and in IT related systems. Let's now try to discuss some strategies how to deal with complexity in software, but also in organizational aspects. And again, I think we do not have a lot of deeply established best practices, but there are some ideas that I would like to forward and that can provide food for discussion, and that you hopefully can contemplate for your own company, discuss with colleagues, and maybe could help you in managing and structuring your systems a bit better in the future. There is quite a nice book and presentation by the late Peter Kruse, and he asks, how do people react to complexity? What are typical strategies people try to apply when they come across a complex situation? And then he discusses what works well and what does not work so well. Let me give you some things some strategies that do not work so well. What is one very popular one? Well, ignore it. Ignore the complex problem. Ignore the situation. Well, as we know, sometimes ignoring a problem, it goes away. Sometimes. But often it does not. And when it does not go away, it can become much bigger and much more problematic. So ignoring it is not always, let's say, or often not a good advice. Second one is trial and error. Trial and error generally does not work well in complex situations. Why? We have too many degrees of freedom, and also something I said in the beginning with wicked problems, you cannot try again from the original situation, because with the attempt, you change the original system, and now you're in a different location. So you cannot try and then fail and come back to the original place. So this is a significant issue. And now a big one is rationality. Try to understand and predict the system. So this is the classical management approach. No, we have to analyze it, and when we understand it, we make a clear plan, and then we solve the problem. This is pretty much a modern myth. Complex systems cannot be understood and predicted well enough to be certain what effects particular changes will have. This doesn't mean that you can do nothing, but the idea of a detailed understanding and then a rational decision and clear plan that will be successful, this idea is misleading and will not work. So, in other words, top-down, long-term planning, and especially predictions, command and control, will not work well. And by the way, as a maybe general remark here, if you look at this quite qualitative graph, I think what we are doing here is also, maybe you can think about that, our capabilities to handle technical systems and software systems certainly is increasing or was increasing over the last decades. We have better tools, we have better processes and so on, but we are not using the better tools, the better processes to program systems like we had in the 80s or 90s. No, we are constantly making systems that are more complex. In other words, what we're constantly doing is actually the complexity of the systems that we are building seems to increase faster than our complexity, than our capabilities. And this, of course, is quite a mismatch that can be quite problematic. Right, now let's move from what does not work to what generally works or what can work in certain conditions. So one thing that Peter Kruse mentions is reduction to a few criteria. That's actually an interesting one that can work in certain conditions and can backfire in a big time. When can it work? For instance, you probably know it from your personal life. Let's take me for example. I have not a lot of clue about cars. I'm not interested in cars, I don't care. If I would buy a car, I would be certainly overwhelmed by all the technical details these various types and manufacturers and whatnot have. So I would certainly not go and compare the technical details. I would probably reduce the problems to a few, the problem to a few criteria. For instance, cost, brand, and some characteristics that I wish for the car. For instance, how many people should drive, how much luggage I want to have, and maybe some technical features that I would like to have. So I would reduce the criteria, cost, performance, brand, maybe something like that. And then I would just see which cars fall into that particular criteria. That can work, but it can also backfire significantly. We all know the old saying, no IT manager was ever fired for purchasing. You can now enter the name of the brand. So it is a common but often not very good IT strategy to, let's buy what the others buy, because then at least I cannot be fired, because I can always say, well, I bought what all the others bought, right? So, well, that may be safe for me, but is not often a good decision in sense of architecture in that sense. So reduction to a few criteria can actually backfire. What can work quite well is intuition. Why intuition? Well, intuition is nothing else than someone has a lot of experience. This means sort of pattern recognition. So this is like chess. Like a chess master like Magnus Carlsen is not thinking 100 times faster than I'm thinking, but has a lot of experience. He has a pattern recognition about situations and much better understands in a few seconds what are the important characteristics of the situation. And this is a similar thing that can happen like in management decisions, in IT decisions. Someone who has a lot of experience in similar systems, that's very important, who has a lot of experience in this particular domain, can often take very good intuitive decisions. Another approach that can work quite well is what is sometimes called sense and respond, or seed, select and amplify. I also have the references for that in the notes. So what does that mean? Let's have a look at this figure here. The idea is, when we don't exactly know what works well, then, well, in fact, we should allow for some experimentation. So we try out different things. Educated guesses, not randomly, but educated guesses. We try out different things. For instance, if you have a company and maybe you have different branches, you could probably try out different things in different branches. Seed, this is seed, you try out. Then you observe, you select what is working, what is not working. What is not working, you dismiss, and what is working, you select and amplify. And then you go here in a circle. And you iterate again. So you go ahead and hopefully improve the situation step-by-step, iteration for iterations. As far as software systems go, I think we should generally reevaluate the metaphors we often have in our head. We often have technical metaphors in our head that are not actually helpful for our situation. For instance, as I mentioned before, let's forget the idea of a project, right? Why? What is a project in our definition? Project is usually defined as having a fixed start, fixed end, fixed scope, fixed budget. None of this is true for IT. Why? Well, I personally would rather like to suggest not the technical image of machinery of the 19th century, but more like an biologically inspired or gardening inspired example. If you look at this illustration, for instance, it's not about the details here, but let's see, this is like a biological ecosystem. We have mangroves, we have land, we have seagrass, we have coral reefs and so on. And the interesting part here is none of those biological entities, the animals, the corals, the plants, the mangroves, are working isolated. They work in interaction with each other. There's not a project. Like once there are mangroves, they interact with the other systems. Now imagine a garden. Imagine you plant a garden. Now it's not like enough to just plant some roses there and some bushes here and then go away. No, you have to figure out the moment. Once you have the roses there, you have to maintain them. You have to put enough nutrient in. You have to put water in there. So you have to go through your garden regularly to take away stuff that doesn't belong there, to clean up and so on and so forth. So, and this is pretty much, I think, the same thing that we have in a software ecosystem. It's like software gardening. I like this image very much. It's like the idea, you plant a new module, you plant a new system. As soon as you put the system in place, like here the seagrass, the system will start to interact with the other systems. And suddenly you have a connected system. And you better know what each of these modules are doing and do not lose overview and also the capabilities, the know-how to manage this. And it's also interesting from another point of view. Again, John Gall says one interesting thing. He says, a complex system that works is invariably found to have evolved from a simple system that worked. So this means very often complex systems that work start from smaller systems that you step by step evolve towards bigger systems. So you evolve your knowledge, you evolve your workforce, you evolve your expertise, and you evolve your system. Top-down definition of complex systems tend to fail. So we need sort of evolutionary change, ecosystem approach, iterations, feedback loops. Two last aspects I want to mention is, one as mentioned at the beginning, and this is failure. We said it's very hard to predict how a complex system works in the future. And so it's also very hard to, or actually impossible to create a complex system that works without failures. So failures will be a standard procedure, if you will, a standard thing that happens. Now, Nassim Taleb said one very interesting thing. He said, the redeeming idea is simply to ensure that human and computational errors remain limited and to prevent them from spreading through the system. Like this illustration I made here, this short video, what we want to avoid is that one part of our system falls and it takes down the whole system. That's not what we want, right? So this means we should try to build systems that can handle failure of each individual component. One good example for that is Netflix with the Chaos Monkey. Netflix has, I don't know, thousands, 10,000s of servers and components, and they realized quite clearly that it's impossible to run 10,000s of components and guarantee that all of these components are running at all time. That's not happening. Any of these components will fail anytime. So if you already know that this is going to happen, well, then let's build a system around that. We build a system so that any component can fail at any time. And so they said, okay, well, let's make it properly. Let's build something that's called a Chaos Monkey. Chaos Monkey is a system that in production randomly turns off particular components. This means every programmer at every point in time is aware that any component can be turned off at any point in time. So this means you have to program your systems in a way that you're not entirely reliable on the functioning of any other system. So you have to have built something that is like graceful degradation into the core of your system. Similar considerations we have in security, for instance. There are security experts who says, consider you are hacked. Just don't assume you can make your system completely waterproof. Assume you're hacked. What does it mean? Any of your component could be hacked. What does it mean? How can you build your system so that still, even if one part is hacked, not all falls with it? So that's a different mindset. And of course, if you want to evolve systems, you also have to evolve and keep the knowledge of the system. You have to think about retention of employees, retention of experience, know-how sharing, for instance, using practices like pair programming or code reviews. And timing and speed also play an important role here. And as a wrap up in the end, I would like to introduce something that I like very much from Stuart Brand. Is a concept that he calls pace layering. And read this article, that the link again is in the notes. And this is a figure from the article, and I like it very much. You see, he builds up a system of layers. On the bottom is nature, then we have culture, governance, infrastructure, commerce, fashion. And the idea is that the layers increase in speed. So nature is evolving the slowest, then we have culture, then we have governance, then infrastructure, commerce, and so on. And the idea here is each layer must respect the different pace of the others. So infrastructure is sort of dependent on the speed of the governance and is, on the other hand, influencing the speed of commerce. And he says, in a durable society, each level is allowed to operate at its own pace, safely sustained by the slower levels below and kept invigorated by the livelier levels above. So there's sort of a tension between speeds, but they can invigorate each other from top down, and they can safely sustain slow levels from below. And I think that's a very interesting idea. And why is that important? Let me give another quotation from this article. He says, fast learns, slow remembers. Fast proposes, slow disposes. Fast is discontinuous, slow is continuous. Fast and small instructs slow and big by crude innovation and by occasional revolution. Slow and big controls small and fast by constraint and constancy. Fast, and this is now very interesting, fast gets all our attention, slow has all the power. And I think this is a very important last sentence. We constantly talk about innovation, fast innovation in IT, but actually slow has all the power. The infrastructure that we built has to work, has to operate properly, has to be maintained. If we do not maintain our slower available infrastructure, we will not be able to build on top of that new innovation. So in other words, it often pays off to be a bit slower, to be fast in the larger sense of the game. And there's again a very interesting quotation from Peter Kruse. He said, in a crab pot, there's enormous dynamic, but when you look close, you see that actually nothing happens. And that's, I think, everyone knows from companies. There are people and situations where there's a lot of enormous dynamic, people doing stuff, but when you zoom one level out, you figure out actually we're not doing anything really. Nothing is going forward, but there's a lot of dynamic. So let's not be misled by a lot of dynamic. The question is this dynamic also directed into something? So sometimes it pays off to be slow, to be fast. Okay, to end with a quote again from Stuart Brand. Build a thing too fast and mistakes cascade. Build a thing in the right pace and mistakes instruct. Build a thing too slow and mistakes are forgotten and then endlessly repeated in endless restarts. Thank you very much for the attention. I hope it was interesting for you. I'm very interested in comments. Should you have comments to these ideas or suggestions or find mistakes, problems, contact me and we can discuss this. Thank you very much.